Evan, you need to write your test. Great. How did the stuff go over the weekend? That first part was easy, yes. How did the, I mean, like drawing a wavelength? It wasn't difficult. Okay. Basically, I forgot to print this out. I don't know what happened. I always seem to forget something with you guys because I feel like we're ready, and then I'm like, oh shoot, this isn't printed. But anyway, um, so how are we feeling about ground state and excited state? Thumbs up, thumbs down, thumbs in the middle. Thumbs down. Didn't understand it at all? Okay. There's not much to it. I mean, like, let's just take a look at this pencil. Yes? Where is it more stable? There. Yes? That would be the pencil's ground state. Okay? If you're in an atom, if you're closer to the nucleus, then you're in your ground state. That's it. Is good? Are we feeling better about ground state? Okay. Excited state, it requires some energy to be put in. So either you throw a photon at it and that photon bumps it up, or you throw some electricity or some other kind of thing like that. Devasher, yes. Yep. I think it does. I know that the Northern Lights has something to do. Why are you guys talking over somebody else's question? Thank you. I know the Northern Lights have something to do with the plasma state, which is like gaseous ions. And so, but I'm not really 100% sure. That would be an interesting thing to kind of go do a little lookup on. Yeah, yeah. Yes. Yep. No, no. If you input electricity, it'll bump the electrons up. When the electrons fall back down, they always give out electromagnetic radiation. So either visible light or infrared or ultraviolet light's going to come out of some variety or other. Yes. Okay. That's why I don't know. Did in your junior grades, did you see like those little light element boxes where like it's a black box and then there's an element tube and it like goes zzz, and then you can see the light glowing? Discharge tubes, and you wear the glasses and you can see the rainbow. Yeah. Okay, so that's what's happening when you when you see a neon light, for example, you're putting electricity into neon atoms and you're watching the light be released as the electrons fall back to their ground state. Is good? Okay. Let us take a look then at absorption and line emission spectra. This is on page 19. And that is huh? Electricity is just the flow of electrons. Well, not always. It it is a form of energy. So what's happening is that you've got a positive and I don't know. I don't know. That's physics. Go talk to a physics teacher. Okay, yeah, sorry. Yeah, go ask Mr. Donani or somebody. Okay. Page 19, and I want to go to here, and that is, where is it? Absorption and emission spectra, because I need to get the link. We're going to watch the video. Okay? Where's my sound? Sound. Okay, here we go. The boring atom. Yes. Yes. Okay, so Bohr didn't know why, but only certain potential energies were allowed. And that's because when he did those things, like when he looked at the spectrum from one of those, say the neon light, and he looked at the spectrum, he did not see all the colors of light, right? he only saw some colors. And in fact, I feel like we're skipping ahead of the game. We should probably do the one before this. Yeah, let's do the one before this. Here we go. So actually, yeah, let's watch this one. So this is 9.1e. Okay. 9.1e. I'm not sure what page that's on because I'm not that organized, apparently. Sorry? 17. Okay. So let's get this queued up. Oh, I need to turn on the sound. Because this one's a really good introduction to why he thought that. Okay. Oh, please, just load. Come on. You can do it. You can do it, little computer. Come on. Oh, it's trying to load both of them. Let's close this one. There we go.
Section 7.2, the Bohr model of the hydrogen atom. The nucleus is incredibly small and takes up only a small part of the atom, but it is the majority of the mass because it's made up of the protons and neutrons. Now the electrons, on the other hand, occupy a large amount of space but add only a little bit of mass to the overall mass of the atom. Rutherford conducted the gold foil experiment and created the nuclear model, but then Mr. Bohr came along and he introduced the idea that electrons orbit the nucleus like planets orbit the sun. These orbits are quantized. Now what does quantized mean? It means they're
quantized. That's an important word. You'll want to know it. Quantized. I don't know. Let's see. We're on page 17, right? Yes. I don't know where you write quantized. Oh yeah, these orbits, what we refer to as shells or energy levels, are said to be quantized. And we're going to learn what that means. Quant, like quantitative, quantized. Quantized.
There is no in between. The piano is quantized.
Okay,
The nucleus, like planets, orbit the sun. These orbits are quantized. Now what does quantized mean? It means there is no in between.
There's no what?
I need to take a look at
no in between. I don't know how I jumped ahead that far. No in between.
Quantized. Now what does quantized mean? It means there is no in between. The piano is quantized. Only certain notes exist. For example, a C and a C sharp. You can't go in between those notes. Only a C and a C sharp exists. There's no note in between. It's not possible. Therefore, piano keys are quantized. This is a picture of the Bohr model of the hydrogen atom. So let's take a look. Here's the nucleus, and then each of these rings represents a fixed orbit that Bohr proposed. Now these orbits are quantized, meaning there's nothing in between. It's just a specific value for each orbit. So n equals 1 represents the first orbit, and that is always a certain distance from the nucleus. That distance is listed here. The second one is also a certain distance. Now you can't have an electron orbiting the nucleus at 1.5. That's impossible. It is quantized. It must be at 1, or at 2, or at 3, etc. This little red dot's going to represent our electron. So, if we have an electron revolving around the nucleus at the closest orbit, that electron has a lower energy compared to an electron that is orbiting the nucleus at an orbit further away from the nucleus.
If this were a hydrogen atom and that were the only electron there, this would be what kind of state? This would be an excited state because it's got more energy.
Yes. So again, if an electron is close to the nucleus, it has a lower energy. If an electron is further away from the nucleus on a specific orbit, that has a higher energy. Now, electrons can release energy or emit energy and fall down to a closer orbit.
So this would be like in your neon lamp. You have excited that electron, you've bumped it up to n equals 4 by using some electricity, and then the electron's like, well, I don't want to stay here because this is not a stable state, so it falls back down. What does it do with that extra energy it had? It releases it. It emits some light, okay?
On the other hand, an electron can absorb energy and move to an orbit further away from the nucleus. On page 253 in your textbook, you'll see figure 7.10. Bohr's model was accepted because it explained
No, not in your workbook, okay? You don't have this. Yours is on page 17, right here, okay?
Hydrogen line spectrum, which is right here. Now, this line spectrum is specific to hydrogen. Every time the electron goes from n equals 6, this orbit, down to n equals 2, that orbit, it will emit visible light, and it will emit it at 410 nanometers. That's the wavelength. If you know the wavelength, you can find out the energy released. The light it emits always has the same amount of quantized energy, wavelength, and frequency. Let's illustrate this one more time.
Okay, hold on. So before we go on from there, you'll notice that we have an electron falling from energy level 6 to energy level 2. And that gave us it could fall to energy level 1, or it could fall to energy level 3, or it could fall to 4, or it could fall to 5. Why are we concentrating on falling to energy level 2? Because when electrons fall from higher orbitals to energy level 2, they are just in the perfect range to emit visible light. And because our eyes work in the visible range, that's what we're obsessed with. Yes? We're like, ooh, a color that we can see, right? So when Bohr was working with this, what could he see? He could see these visible lights. So he saw in the spectrum some violet light. When you fall from 5 to 2, you get a longer wavelength. What does a longer wavelength correspond to? Less energy and a lower frequency, okay? And you can see, of course, the difference there is a lot less. Here we have a larger difference, here we have a smaller difference. When we fall from energy level 4 to energy level 2, we have an even smaller distance and we're getting a longer wavelength yet. Yes? It jumps directly. No. No. If it's jumping from 6 to 2, it's in 6 and then it's in 2 and there's nothing that happens in between. Okay? And that's why you get that particular band of light, because if it did go from 6 to 5, then you would see a wavelength that corresponds to this amount of energy, which is a lot smaller. Yeah? Yeah. So we have to get all that energy out to, yeah. Now, what color, what type of electromagnetic radiation do you think we might get if we fell down to energy level 1 instead of ultraviolet? And what if we fell down to energy level 3, infrared? Okay, because we're getting lower energy amounts. Now, of course, there's some overlap in there, but that's sort of kind of how it works. Okay?
If I have an electron in an outer orbit, and that electron moves to a closer orbit to the nucleus, it will emit energy. Compared to an electron that begins at an orbit closer to the nucleus and moves out.
What did that have to do with energy? If it starts low and it moves high, what did it have to do? It had to take in energy. It had to absorb energy.
That will absorb energy. That brings us to an equation where we can talk about the change in energy. The change of
This is like a hugely simplified equation. There is another thing we'll look at, but this is the simplified version, okay? Yeah, basically it's final minus initial like every other change, okay? There is a much more complicated equation for actually calculating the energy, but you are no longer required to do it for AP, so I am no longer teaching it, okay? If you're interested at any point, it is in the big black textbook, but you are not responsible for it. So we're just gonna go with this. AP will not even ask you to do this because it's not a real formula. Okay, it's kind of like a wishy-washy version.
Energy equals the final energy minus the initial energy. If that's the case, what is the change in energy for an electron going from an outer orbit to a closer orbit? The change in energy should be negative for an electron going from an outer orbit to a closer orbit to the nucleus. Let me illustrate that. If we start with a higher energy, let's give it an arbitrary value of 4 joules. Okay, so I started on an outer orbit further away from the nucleus, and I ended, my final energy is much smaller because it's closer to the nucleus. We'll give that a value of 1. 1 minus 4 equals a negative 3. My change in energy is negative for an electron that is going from an orbit out here to an orbit closer to the nucleus.
So this is very similar to your enthalpy, right? If your change in enthalpy, if it goes from higher enthalpy to lower enthalpy, it must be negative, right? And that means that it is releasing energy. This is exactly the same thing. It's emitting energy as light.
Energy, though, should be the absolute value. So the change of energy is negative for that example, but the energy should always be the absolute value.
And this is like when we talked about how much heat is released, right? How much energy is released. We're not going to say, oh, negative 36 kilojoules was released. We're going to say we released 36 kilojoules. So just similarly like that, these energies will also be absolute values. Okay, when we're not talking about the change in energy, but just the amount of energy of, like, say, a photon that's emitted. Okay.
So the absolute value of negative 3 is 3. Now these are just example numbers. You'll be dealing with numbers that are much smaller. Here's an example problem.
Okay, we're not doing this. Okay. There we go. There's some questions. We'll let you do that another time. Actually, do you want to take the moment to do them? Take a moment to do them. Page 18.
In this video, we're going to look at absorption.
Are we done? Can we carry on? Carry on? Okay, page 19.
Absorption and emission line spectra. So we'll view of the Bohr model of the atom.
There we go.
In this video, we're going to look at absorption and emission line spectra. So we'll start with a quick review of the Bohr model of the atom. The protons and neutrons are located in the nucleus of the atom, and the electrons are located in energy levels or shells around the nucleus. Electrons can only exist at
What? Did it just start to clear up? What?
Oh yeah, we were like,
Oh, that. Okay. Electrons can exist at certain energy levels with discrete amounts of energy. What does discrete mean? Specific. Okay, yes.
at certain energy levels with discrete amounts of energy. So an electron can occupy energy level 1 or energy level 2, but not in between energy level 1 and 2. The next point is that electrons can transition between energy levels.
Did we get that? Electrons can transition. Yes. Yeah. I don't know. I'll look it up for you. Okay? How's that sound? I think they get smaller and smaller. I think this one's more correct.
So that means an electron can transition from n equals 1 to n equals 2, or from n equals 3 down to n equals 1. If an electron absorbs a discrete amount of energy, it can transition to a higher energy level, which is called its excited state.
Did we get that? If an electron absorbs a discrete amount of energy, it can transition to a higher energy level or an excited state. Can you fill in the next one without even reading it? What does it say? If an electron emits or releases, I would go with emits because we are talking about emission spectrum here, a discrete amount of energy, it can transition to a lower energy level. Excellent.
So for example, an electron can absorb a discrete or exact amount of energy, and it will transition from an n equals 1 to an n equals 2 energy level. If an electron emits a discrete amount of energy, it can transition to a lower energy level. So for example, an electron in the n equals 2 energy level can emit or give off energy and transition to an n equals 1 energy level. So next we look at how these electron transitions between energy levels give rise to absorption and emission line spectra. So here we have again the Bohr model of the atom, and here we have an electron in the n equals 2 energy level.
And why are we focused on n equals 2? Visible light, and we are visible people.
And these arrows show the electron transitioning to the n equals 3 energy level, the n equals 4 energy level, the n equals 5 energy level, and the n equals 6 energy level.
And if you wanted to for yourselves, you know, you go home, you can like color them in red and blue, and you know what I mean? Because then you've got like the red, which is the smallest transition, and the purple, which is the biggest transition. I do have pencil crayons if anyone wants to borrow any at some point. They're just on top of the microwave. Okay. You can always go back and like look at them later. Okay. Is that a hand? Yes. He didn't. If you throw electrical energy, they're going to transition from every energy level to every other energy level. But the only ones that he'll be able to see are the visible ones. Yeah? Yes. Sorry? It's special only because the transitions to energy to and from energy level 2 are in the visible spectrum range, so that we can see them. Yeah, there are all kinds of other transitions. Yeah, there is some overlap. Yeah.
And here we have an absorption spectrum. You may remember this from the previous video. An absorption spectrum has black lines on a colored background.
Okay, so we're going to be exciting these electrons by throwing white light at them. Okay? In this case, we're not exciting them by using, electricity. In this case, we are throwing white light at them. And the white light, as it passes through, if you then split it with a prism, you'll see that there are gaps in what comes through after it's been shone through the element. Okay? There's a gap here, and a gap here, and here, and here, because those are the wavelengths that have been absorbed as those electrons transition upward. Yes? This is hydrogen. So these are the line spectra that you would get with hydrogen. It's going to be different for every element. Yes. There are, however, when you start putting electrons into orbits, or orbitals, we're going to call them, they start repelling one another, and then that changes the distances from the nucleus. And as you'll find out very, very soon, a shell is not a monolith. It's not all the same when you get into multi electron atoms. Okay? It gets fancier. Okay? Just hold on to that. We'll get there. Okay? Yes. Yeah. Yes. Well, yes. In fact, they all have as many shells as you could possibly want, in theory, right? You know, I mean, we have elements that have in their ground state occupied up to n equals 7. That means that n equals 7 exists for all atoms. You can excite electrons up to it. I don't know, there's probably 8 and 9 and 10, but we don't really deal with them because those aren't present for ground states. Yes? Yes. And that's called ionization energy, because you have now turned it into an ion by making an electron go away. Yes? And we will be coming up on that shortly. Yes. Yes. Yeah, it can go into yeah, I mean, things are going to be jumping up and down from all of them, so there will be an empty space in some of them at some point. I don't think so. No, no, you cannot. That is not allowed by physics. Okay?
Below our absorption spectrum, we have the energy levels of the atom from n equals 1 to n equals 6. And as you can see, the colored arrows on the diagram, they correspond to the colors that are missing from the absorption spectrum. As we mentioned earlier, electrons can transition between energy levels if they absorb discrete amounts of energy. So if we start with this red arrow here, the electron has transitioned from the n equals 2 to the n equals 3 energy level, and the energy that the electron has absorbed corresponds to the wavelength of red light. Next we'll have a look at this blue arrow here. The electron has transitioned from the n equals 2 to the n equals 5 energy level, and the energy that the electron has absorbed corresponds to the wavelength of blue light. So to summarize, the reason for these black lines on an absorption spectrum is that the electron transitions between n equals 2 to 3, or 2 to 4, or 2 to 5, or 2 to 6. The electrons have absorbed the energy, and the energy that's absorbed corresponds to the wavelength of visible light. So in the previous example, we saw how electrons can transition to higher energy levels when they absorb energy.
So absorption and emission spectrums are just like two sides of the same coin. Okay, essentially you're getting the same colors. It's just in one, they're showing up as black lines because they're absorbing that from the white spectrum. And here they're going to show up as lines on a black background.
And the energy that they absorb is related to the wavelength of visible light. One thing you'll notice about this diagram is that the arrows are going in the opposite direction. So these electrons are transitioning from higher energy levels to lower energy levels. And again, each electron transition has its own color. So here we have our emission spectrum, which has colored lines on a black background. So here we have the energy levels within our atom from n equals 1 to n equals 6. So we'll start with this red arrow here. This red arrow represents an electron transition from the n equals 3 to the n equals 2 energy level. When an electron transitions from a higher to a lower energy level, it emits a discrete amount of energy, and the energy that is emitted by the electron corresponds to the wavelength of red light. Next, we'll have a look at this blue arrow here. This blue arrow represents an electron transition from the n equals 5 to the n equals 2 energy level. And when the electron transitions to a lower energy level, it emits energy, and the energy that's emitted by the electron corresponds to the wavelength of blue light. So to summarize, the reason for these colored lines on the black background of an emission spectrum, they correspond to the energy emitted when an electron transitions from a higher energy level to a lower energy level, and in this case the energy level is n equals 2. Next we look at the hydrogen emission spectrum. So here we can see the different types of electromagnetic radiation.
So this is just, because, we are focused on visible light, but this is to point out that it's not just all visible light. We have our UV over here. Okay, we have our visible light, and then we have our infrared. Yes. Yep. Screen, something. Yeah. Probably, but we're not going to worry about that. I'm going to assume that people, not theoretical physicists, practical physicists have worked out this problem. The engineers have done their job. I don't know how they did it because that's not I just trust that it happens. Okay? Yeah.
Emitted as electrons transition from higher to lower energy levels. We have UV radiation, visible light, and infrared radiation. So we'll start by looking at electron transitions to n equals 1, which is the ground state, and they correspond to UV radiation. So UV radiation is the highest energy, it has a high frequency, and a short wavelength.
Now, when we say it has the highest energy, obviously there are forms of radiation that have more energy, but this is the highest you're going to get from transitions within the atom. Yes?
Next are electron transitions to n equals 2, and they correspond to visible light. So in visible light, violet is highest energy, red is lowest energy. In addition, violet light has the highest frequency and the shortest wavelength, red light has the lowest frequency and the longest wavelength. And finally, we have electron transitions to n equals 3, and that corresponds to infrared radiation. So infrared radiation is the lowest energy of all three emissions, it's the lowest frequency, and has the longest wavelength. In this video, we're going to look at absorption.
So if we had an atom where the electron could be at any distance from the nucleus, would we see these line spectra? No, we would see electrons absorbing any amount of light, right? And emitting every amount of light. So when we saw an emission spectrum, instead of seeing these bright lines at certain places, we would see the entire spectrum, because it would be able to absorb however much and emit however much it wanted to, if those electrons were allowed to be anywhere. But they're not. They're only allowed to be at this distance, or this distance, or that distance. That's why we know they are quantized. Electrons can exist in those energy levels, but they cannot exist in between those energy levels, which begs the question, how do they actually move from one to the other without passing through the space in between? It is weird. Small stuff is weird. And actually, if you're like me and your brain goes a little foggy when it gets to this kind of weird stuff, you can just be like, small stuff is weird, and just kind of go with that. We can kind of explain it by the electron wave particle duality. Oh, what? Electrons are particles, but they are also waves. When you look at an electron, and you have to look at it by doing something to it, you smack it with something, whatever, okay? So you're looking at an electron, it takes up a certain position in space, and you can say, ah, there it is a particle. When you are not looking at it, it behaves like a wave. Not like a particle. It behaves like a wave. Schrödinger, yes. Yes, it's all about Schrödinger. And in fact, would we like to watch a little video about Schrödinger and stuff? Okay, this is on page 43. Okay. Page 43. And I'll have to pull up this video too. So if you wanted to do the questions on page 22 while you're waiting for the video to come up. There's questions on page 22. I'm pulling up the video. It'll just take a moment, because you know how this computer is. It's like,
Quantum mechanics and the shape of atoms as described.
Oy, so loud. Okay, so this is just to give you a flavor of what is actually happening in the atom. But it is a 7-minute video, so when I say a flavor, I really mean just a little taste, okay? But I love this video because it sort of just, it tells it like it is, but it simplifies it to a point where you can kind of be like, all right, sure.
Quantum mechanics and the shape of atoms as discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves.
Hang on a second, I'm just going to... I don't know, is it better if I... There, let's try that.
And interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, Duality, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were theorizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. The core was really small. A typical atom is about 300 picometers across, whereas the core is typically 0.01 picometers. So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space, if they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom, basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at these experiments was a Frenchman called Duality, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as...
So the electrons are interacting. We've smacked it with a photon. We've made it crash into a detector plate. It behaves like a particle. So basically, when you're looking at it, it looks like a particle.
Hard little balls of matter, kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stopped messing around with the electron, it would suddenly fall apart into some sort of wave function.
Did you get that? The particle falls apart into a wave function. Oh, small stuff is weird.
Some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found.
So it's kind of predicting where the electron is going to be. Okay, it's a probability field.
This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So they needed a new model, but they realized that this model couldn't come from classical mechanics, because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that
what kind of mechanics? Quantum mechanics!
Included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation.
Showed up in my first year university textbook, and I was like, I think I peed my pants a little bit, probably, you know? Like, it was scary. I was like, what is that? You do not need to solve this equation this year. Just letting you know, okay?
Nowadays,
not next
we
year
simply
either.
know it as the Schrödinger equation because it was the rock-solid core on which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron.
Okay, this is the easiest atom, just one proton, just one electron.
And that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen.
Okay, so he did the math. And you know all that stuff you do in math where you got graphs and you got axes and you're thinking and then blah, 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 blah. Okay? So, I tell you, I don't stand any chance of ever understanding what's truly going on here because I cannot grasp at any level what's happening in the math there. It's not going to ever happen for me. So I'm just like, okay, electrons, sometimes particles, sometimes waves. If you interact with them, they are particles. If you leave them alone, they are waves. Yes? I believe so. I believe photons are also particles and waves. Yes. Yes. Ha 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 ha. Isn't that awesome? So these are the orbitals of hydrogen. So this is what we call an s orbital. This is shell number 1 contains this orbital. Okay? Shell number 2 also contains an s orbital. S stands for sphere. Okay, you see how this is a sphere? But it also contains 3 p orbitals that look like this. And this is a space that electrons inhabit. Okay? So if you have an electron in shell number 1 of hydrogen, it is going to appear somewhere within this sphere. When you're not looking at it, the electron is a probability wave that takes the shape of a sphere. When you look at it, it becomes a particle that exists somewhere within that sphere. Okay? Yes? Yeah? Exactly, right? Yeah? Okay, so we're just gonna take a little look at the rest of this because it will get to some of those questions you were asking and not like make you happy about it, but make you a little less unhappy.
So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby-shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with the proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these 3 blobs together form that one orbital. They house that one single electron.
Okay, so for hydrogen, you just have 1 electron. If you had 2 electrons that were inhabiting that orbital, they would both be within that orbital. Each orbital can hold a maximum of 2 electrons. Yes? It is all the shapes. So when it's in its wave form, it's like those 3 shapes. Okay? And then when you look at it, boom, it's in one of those shapes somewhere. Yes. Okay, here's the thing. It is that shape. It is that probability field. But when you look at it, it essentially condenses to a particle that exists within that shape. As far as I know, it's random. Yes. Like making it interact with something, shooting a photon at it. Like, I don't know what the particle physicists actually do, but they do stuff. Yes? Yes. None of these are actually flat planes. These are kind of like 2 balloons with a gap in between them. They're just hanging out there. I mean, the entire atom will spin in space, right? The atom can move, it can be moving like this, it can be moving like this. With it, yes. Okie dokie. Okay, let's watch a little bit more, and then we'll answer more questions.
And this one makes a
The shading is trying to make it look a little bit like 3D. Yeah. These are all three-dimensional structures that we're trying to draw in 2D.
fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape. And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron. If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense. But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dice.
So, if Einstein was unhappy about this, I don't expect to ever be truly happy about it. Yes? So, if you can come to some sort of... Actually, I was talking with my dad about this because he was a physics teacher, and he's like, if you think you actually understand something, you probably don't. What you have done is you have come to, but you can come to a level of comfort with it. Yes? So don't try to necessarily understand everything that's happening. Try to come to a level of comfort with it, because unless you can do all that math and truly like have a feel for that math, your chances of understanding it are slim to none, because I know I'm never going to truly understand. But I feel comfortable with the fact that electrons are a wave and they form a blob. It is a blob, and then it is a particle, and then it's a blob, and then it's a particle. Yes. Yes. It is part of the n equals 3. There's actually a sphere at n equals 3. There's the two balloons at n equals 3. And then there's this thing as well. Okay?
But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what the electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them. So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Yeah, the third shell is made up of a whole bunch of orbitals. Yes. Yes. So, yeah, so a shell is things that are in a hydrogen atom, all their energies will be the same. They will all be the same. But once you start putting electrons in, like he was saying, these things distort one another. The electrons repel and they distort them, and they make the different orbital shapes have a different energy level. like a smaller energy level. So within energy level 3, you have the sphere-shaped ones, you have the 2 balloon ones, and then you have the ones that are kind of like the balloons in the donut, okay? And the sphere-shaped one is the lowest energy, okay? The 2 balloons, that's a little bit higher energy. And then when we get into the other ones, those are even a little bit higher yet. And we will be looking at all of these in a lot more depth starting next class. Yes. Yes. Yeah. What does it mean to not move? It would have to take on a different wave function. It would have to be a different blobby shape. Yes. Uh-huh. Well, you have each orbital can actually accommodate 2 electrons, so you would have 4 different orbitals. We're getting ahead of ourselves, okay? We're gonna come back to this. Next year we're like totally out of this. Boom, gone. It's all quantitative stuff next year. So we're not worrying about the atom next year. Yes. Each orbital can contain a maximum of 2 electrons. Okay? So this is when I wish for a long block because I feel like we could just like go like crazy, but that's okay. You need a break too. So let us get out of here for a moment. And we're going to look at another model that helps bring this back down to a level that makes me comfortable. Okay? So we are on page 45. Okay? Page 45. Where's 45? Here we go. All right. So now, have you guys heard of standing waves, seen standing waves? This is page 45, 45. They're not. Okay, so what I want you to look at, and this is rather than thinking of a wave as a blobby shape, you can think of a wave as something like, you know, a nice sine wave or something like that. And you can imagine, although this is not what really happens, that this wave goes in that circle, right? Like a Bohr model. Oh, isn't this nice? We're back to Bohr, which seems like so comfortable and homey right now, right? Now, if you have a wave that doesn't fit perfectly around the atom, that is a not allowed state, okay? If you have one that perfectly fits to just a perfect number of wavelengths, this one would be what, 1, 2, 3, 4, 5 wavelengths, then that is allowed. So that's what we mean when we say they're quantized. Those give you the allowable states. So a standing wave, have you ever done something where you sit there with like a rope and you jiggle it up and down? No? Yeah, like a jump rope. If you get it going like this is called the first harmonic, and that will be stable, okay? If you try and do this, it's going to go all wobbly wonky on you, okay? This is going to be another stable state. This is going to go all wobbly wonky. Stable, wobbly wonky, stable, wobbly wonky. Now, what the heck does wobbly wonky mean? Let's take a look. Okay, we have a video here. Another video, a standing waves video. Yeah, There we go. I am going to recommend, but not require, that at some point, when you're feeling like you have a little bit of extra time, you hang out. Why did that not click to anything? There we go. You sometimes hang out in the big black book for a little bit, okay? There's going to be stuff in there that you don't need to know, but it does sort of dig a little bit deeper. So some of those questions that you have might get answered, okay? Pick a point in time where you're like, I feel like I have enough to have a lot of questions and I'd like some answers. Go and read it. If you're not at all interested, if you're like, I am happy with the wibbly wobbly Ms. Spence explanation, then just stick with that because that's all you need. Okay? Yes. Pretty sure they know it. Like it's called quantum theory, which means when something is a theory, it's like pretty well backed up. It's like, I mean, do we know anything for sure? I mean, gravity's a theory. Do you know what I mean? Like, right? Yeah. Yeah, well, I mean, there's string theory, which I don't understand even a little bit. Like, I know that there's a thing called string theory. That's my knowledge of string theory, okay? Oh, come on. Oh my God. Oh. Oh my God.
Interruption. Kara's name goes to the music office, please. Kara's name to the music office.
I was afraid it was going to be me. I thought Karen. Because you guys know I'm a Karen, right? Ah. And sometimes it comes out, right? Oh, come on. Oh, here we go.
Frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave deflects, comes back. Now, if I set it to just any old frequency, let me just turn this on.
Can you guys wait for 1 minute? Okay. I'll put the homework up on Teams, okay?
Will Perkins to the office. Will Perkins to the office.
So it's sending waves back and forth, but these waves are out of sync, if you like. They're not consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
Isn't it?
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, this is a node, and the middle is a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be
Wibbly wobbly, not allowed, allowed.
And there we go. It's basically the scenario of a jumper. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5 is 25. And there we go.
Okay.
So that's the...
We're going to leave it there. Thank you so much for staying. We can watch the rest of this next day. Your homework will be on Teams.
Miss Ben. Hi. Hi. So I did a requiz on Absorption, and I wanted to ask if you marked it.
No.
No, oh, that's okay. Sorry about that. Take your time.
No, it's okay. It's okay. I've just been like, okay, I'm just going to mark this bunch of tests.
Oh, okay.
So,
okay.
yeah.
Okay. Thank you.
No. Yeah. Hi.
You know how when you guys on 2 to 1, it's like red,
Yes.
the color, and 3 to 1's like blue or something like that.
Or rather 3 to 2 and 4 to 2 or whatever.
Like, how do you get the colors in between? Because there's no you can't go in between the.
No, you can't. So in multi-electron atoms, we don't just have those single energy levels. We'll have different ones depending on what the atom is. And so that's why different atoms give off different spectra. Yeah?
So like hydrogen can only give out.
Hydrogen can only give off those ones, but sodium will give off different ones. Neon will give off yet different ones.
So if it goes from like 2 to 1, it can't give out any other color other than red, right?
Yeah.
Okay.
Yeah. You're welcome. See you. Can I help you find something? What are you looking for?
My water bottle and it's downside.
What is it?
I put it.
So your pencil case.
I just put it down. Now it's gone. I thought it was.
It's not in your bag.
I don't think so. I
Okay.
checked.
Maybe someone took it by accident. Because I know I walk off with things that aren't mine all the time. What happened? I once accidentally shut this before. Because I was like, no, it's in the store. And I was like, halfway across the mall and like, oh crap. So I still took it back. Like, trying to sneak it back in so they're like, don't know what I'm taking. Probably. Yeah. Yeah. They will eventually get to mold. They're not there yet.
So they'll have to take it.
They look at the mold.
And then, but they're testing.
Yeah. And they won't get as far. They're not moving this.
But us, we get the
Yeah, I think we
get still.
yes.
Yeah.
you would find your change in volume. Yeah, so if it's too far out, you won't go that one out. Yeah, so if like this was 6, 10, 12, 12, okay. So we average, and then yeah, you know, yeah, hopefully. Yes, yes. So you have a 3.5 gram sample, but you only have 3.37 grams of the actual substance in it. The other 12 grams is like, yeah, 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 yeah. That's good. Yep. How to balance them? Yeah, you got that? Yeah. Good. Enough reactions. Yeah, exactly. That's good. Yes. Yeah. Yeah. Oh, well. Sounds good. Is English your second language? Your first language? Third language. Well, my God, then you should just get extra credit for that. I don't think it's one language. Yes, but I've been speaking it since I was born, so I should be. I should be at this point, right? I'm not good at. Yeah, but you've like kind of gone from like looking to you've had time to like, you know, get out of one and into another. Yeah, so everything's probably just a bit of a mismatch. Yeah. Yeah. So when do you think is like all three? Right. Yeah. 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 Apparently there are people who don't hear words inside their head. Yeah. They don't have an inner dialogue. They think it's certain other things. Yeah, and others like it's so bizarre. It was like a thing that went around the internet. People were like, what kind of weird brain do you have? Yeah. I know, and I'm like, how do you? But you know, these are bright people who do all kinds of things. They just visualizing so like everything in their head works so differently. And we don't know. They're just walking around talking like us, and they're like, oh, I guess we don't talk about that. We have a conversation. And you're like, wow, that is not your power either. And it like wakes you up at 2 in the morning for the next like 30 years. Right. Yes, it is 30 years. You have 30 more years to wake up for that conversation. But it'll have that. It's a conversation. I know, right? I always went, oh my God, I just cried. No. Why? No. You're welcome. Always a pleasure. And after finishing this assignment, there will be one more assignment and then the final test. Very good. Yeah, so I don't want to finish it before December. Yeah. Okay, thank you for your help. You're welcome. was gone for a while and ran into a former in the hallway. Just back from the okay. Yes? That's okay. And in fact, I made these all just like half mark each, so yes. Yeah. All right. Yeah, we did one there. I don't need anything else. Awesome. Thank you very much.